Hi and welcome to the final topic of this course. Good to get to the end of it by now. I'm sure you're feeling that way too. This is on emerging issues, as the exam would call it. There's a lot of information in this video actually. It's not a wishy-washy topic where the exam would have just thrown together the final topic is just some kind of applied stuff. There's actually a lot of information you need to try and consume from this video, and a lot of this information I don't know firsthand. I've had to go away and research it and look it up, read loads of articles, especially on the emerging trends, so that's why it's taken me so long. Although I recommend, especially for these emerging trends, you do your own research where possible. Hopefully if you're revising last minute, hopefully the notes in this video will be useful for you, but it's good to get your own knowledge, I suppose, and read stuff about it. But we'll begin by just, again, I did this in the last few videos, actually showing you a bit more information the exam would have given. So it does ask about how much detail you need to know about these 4 trends. I think it's 4. And they say you need to know 6 to 8 key facts about each of the trends specified and be able to identify any potential issues and impacts of each trend. So 6 to 8 key facts. There's not facts as in the largest quantum computer uses 20 qubits or whatever. It's not those kind of facts, and I think even 6 to 8 is a bit much. You might be stretched a little bit because they're so general topics that it's going to be difficult. And I think the reason why this video is so important and this topic is important because the type of questions we're going to ask you on this topic are not going to be a 1 mark question, a 2 mark question. It's probably going to be 4, 6, even longer mark questions than that. So it's really important you try and get as much information as possible. In terms of, it talks about legal issues, and so you need to know about laws. It says the word they use is aware, and that's a bit unspecific, but the fact that you can get questions about this suggests that you need to be slightly more than aware of them. So I've gone through each of these laws in this video, but that'll be covered a bit later on. So let's begin by talking about the first emerging trend, and that's quantum computing. So this is the development of computers based on quantum mechanical principles. So quantum mechanics is very interesting. You won't have studied it until at the very least A-level physics if you do that, and it's very interesting. It makes you think about the world in a very different way, because really the idea is at a tiny scale, sort of a scale of particles, electrons and so on, the way the world works is very different. So our world works in Newtonian physics, and so according to Newton's laws, like F equals ma and so on, whereas at this quantum level things act very differently. So this is a picture of something called the double slit experiment, and basically it's the idea, and so is this with Schrödinger's cat, that things can be in 2 states at the same time. So in the case of an electron or a light particle, which is a photon, they can act both as a wave and a particle at the same time. So light, I think we generally think of it as a wave, and certainly if we do things like optics, we treat it like a wave. But actually light can act like a particle too, and it kind of acts like both at the same time, so both particle and both a wave. And this is Schrödinger's cat. I'm sure you've heard of it, even though you might not understand what's going on. Without wanting to explain it, the cat, the idea is that outside of a box, if you don't know, I think the idea is there's a 50% chance that this contraption can go off and the cat could die. But outside of the box, you can't know that. So the cat is both alive and dead at the same time. So this is kind of the crux of quantum mechanics. And where this comes into computers is classical computers, also known as conventional computers. They store data in binary digits, bits, as hopefully you know by now if you've watched all the other videos, to 0s and 1s. Whereas in a quantum computer, they utilize something called qubits. And so these are quantum bits. You can see the pattern of conjoining these 2 words, and they can be either 0 or 1 or both at the same time. So this is going back to the idea that an electron can be both a wave and a particle at the same time. This experiment, you'd expect when you fire electrons through these tiny gaps called fringes, called slits, you'd get sort of 2 fringes maybe, but actually you get a interference pattern like you would expect from a wave, whereas an electron you wouldn't expect to behave like that, but it does at this small level. So this actual property of being 2 things at the same time, 2 states, so in this case when we're talking about qubits, 0 and 1, it's called superposition. And the qubits are entities like electrons, photons, as I say, they're light particles, or even single atoms or protons to represent each qubit. So the property researchers often use, property of these particles is spin, and so this isn't literally spin, but it can be visualized as being spin up or spin down, representing 1 or 0, and then it can also be in between. So this is the superposition we're talking about, where it can be both at the same time, and this can be statistically found. So what quantum computers can do is they can massively speed up processing, because you have this third combination. It's not like literally a third combination. It's the fact that you can have both at the same time. Certain algorithms can utilise this, and actually there have been algorithms devised before quantum computers were even a possibility. It's still being heavily researched, but there are things like algorithms designed way before it was even possible, like Shor's algorithm, and they can solve problems not currently possible. So problems that are theoretically possible but we can't solve at the moment are called intractable problems, and quantum computing could certainly help with those. And one of those is about modern encryption. Actually, this in some ways is a disadvantage. So I might have talked about this a bit in the encryption video. A algorithm used widely in encryption is called the RSA algorithm, and this depends on the fact that at the moment it's too difficult for computers to find the prime factors of a very large number. And this means, so if a computer could find the prime factors of a very large number, it would be able to break the encryption. That's how the RSA encryption works. And it would take, at the moment, usually longer than the lifetime of a universe to find these prime factors. For some reason, it's just very difficult for computers to find. However, quantum computers could do this perhaps in seconds, in minutes, in hours, which is much better than the lifetime of the universe, depending on how powerful they are or how efficient they are, breaking this current encryption. So there's just this property of classical or conventional computers. They can't find prime factors efficiently, whereas a quantum computer could. And there are other situations where processing on a quantum computer would be much faster. For simple problems, probably a quantum computer would be much better. So watching a video on YouTube, typing up a Word document, probably a quantum computer wouldn't be that helpful. But for large scale data processing, it could be very, very fast. So a challenge, issue of quantum computing is something called decoherence. And so this is another kind of quantum mechanical principle, and this is just when a qubit or anything loses its superposition. So when you look at an electron behaving like a wave, it will become a particle. It will collapse into a particle. And so if you watched this double slit experiment, you're firing electrons through these gaps. If you looked at it physically, it's not possible because electrons are too small. But if you managed to, it would not look like a wave. You just get two lines at the other side, like you were firing a tennis ball through a wall. Whereas if you're not looking at it, if you're outside the system, it behaves like a wave. So this would break down your system if you're doing it for qubits. You'd lose whatever you're trying to do, you'd lose the information. And so this can be improved by supercooling. It makes the particles slightly more stable, but it's still an issue. But you might have to keep cycling through it until you don't get any decoherence. Another issue is just the general difficulty in controlling these particles. They're very sensitive. They, as I say, decohere at every opportunity, and they're difficult to make, and then you have the large scale costs, and this applies with all emerging issues. Could the costs be spent elsewhere? So unfortunately, I think there was a question on quantum computing. It's one I know most about, which is unfortunate because, like I say, they've kind of used this question up. I don't think you'll get asked about it, to be perfectly honest. You might do. It's not worth risking it. But there's only going to be so many exams. There's only going to be another 2 exams, so they've got other things to question you about. So DNA computing is another trend you could be asked about. I don't know so much about this. I've had to do my own research. So I've done my best. You might want to do your own research too. As I say, loads of articles you could read. That's the main source of my information. So DNA computing uses DNA, as you'd expect, as a material used to make processors in most cases, rather than the ones we currently have, which are based on silicon, although when we look at nanotechnology this might change. But eventually silicon will reach its limits in terms of speed and how small we can make them. That's about 10 nanometers, as we'll discover a bit later. So DNA, in case you don't know, is what carries our genes. So they store the biological information about us. The genes are what code for protein. So genes are like a code. I did biology for a year, and I'm embarrassed to say I've forgotten most of it, but it was pretty much all about DNA and genes, so I should know more than I probably do at the moment. So this information is represented by 4 bases in DNA. So this is adenine, cytosine, guanine and thymine, instead of the 2 bits of information that we currently use, so that's 0 and 1 as we said. So this is what a bit of a DNA molecule looks like. We have this base and they're kind of bonded across like this in this double helix structure. Not really relevant. It was a bit boring without any pictures. So these 4 bases, they're used instead of 2 bits of information, so you automatically have more combinations. So in terms of benefits of DNA computing is that there's such a large supply of silicon, so it's not a major issue about silicon running out anytime soon. But like I say, we are sort of reaching the limit of how small we can make silicon chips. It needs to be very highly purified, especially as the smaller you make it, the more purified it needs to be. And for purifying anything really is pretty expensive. It uses a lot of energy, and the fact that DNA is such a large supply, it's in everywhere, plants, wherever, it's very cheap. So DNA computers can be very small compared to current computers. DNA is tiny. You can see DNA with your there's a chemical process and you can extract it and you can see long strings of DNA. It's pretty cool. But the amount of DNA in your body that's folded up into the tiny chromosomes is pretty incredible. So it's tiny, really. And it can be much better at parallel processing, because if you think about how much is working in your body in parallel at the same time, it's pretty incredible how much is going on without you realising, or in every cell these processes are working. And it's not just DNA we're using. We're also using other things too. So another point, I read this in an article, it may not survive long enough. So DNA does degrade over time, has something called a half-life. You probably covered this in radioactivity. It's quite a longish half-life for biological processes, although DNA is continually repairing itself and replicating. So like I say, DNA computing isn't just about DNA, although this is usually the information storage. So you might also use other things like enzymes, which we've learned about these in biology at GCSE, and they can also be used in combination with DNA. I've heard sometimes it described as enzymes being the hardware and the DNA being the software, so that's what the information is being stored as. So that might be a better way to think about it. And so the other advantages of this technology is it's evolvable. DNA can evolve, we evolve as humans. It's self-replicating, self-repairing, and it's also responsive to external stimuli, so it can change based on things like temperature and other things like that, which normal computers couldn't do. So this makes it a lot more complicated in many ways, and it's very difficult to set up anything to do with DNA computing, but a very difficult problem. It might take a long time to set up, but it might be very quick in the end. Although a simple problem is difficult, it's awkward to use for chemistry and so on to use for DNA at the moment, although at some point in the future it may well be built into our normal computers. So the third trend you need to know about is artificial intelligence. I'm sure you've heard of it. This is the study of creating machines and software exhibiting signs of intelligence. And the aim, at least for the engineering side of this, is to build autonomous machines. And these are machines that can carry out complex tasks without humans' constant involvement. And these are what is known as intelligent agents. We talked about the multi-agent something in a previous video, which was slightly weird, it was slightly out of place, but this is kind of what we're now talking about. And these take in and respond to external changes, like the external stimuli I was talking about a couple of seconds ago. So some robots, which should be counted as an autonomous agent, have the ability to learn in a limited capacity at the moment. In the future, they may well be able to learn a lot better, so they might mimic the actions of humans. This is the most obvious robot. First, when I think of a robot, I think about Asimo. Been around for, I think, since 2000 now. It's pretty incredible. He's not really a artificial intelligence, you'd say, but that's just an image of a robot that comes into my head. So some AI is built to try and replicate properties of our brains. And in the news recently, you might have heard of Google DeepMind beating this man here at Go, which is a game that's a lot more complicated than chess. Chess was beaten by an AI computer, I think, in the late 90s. And so it beat a world champion at Go. And DeepMind is a British company now owned by Google, so I don't know what that makes it now. And their technology uses neural networks. So in our brain we have these neurons. It's incredibly complicated. We don't really, well, I don't personally, but researchers, neurosurgeons don't understand everything about our brain. So it's not like we can totally replicate the brain, but we can use graphs and at a basic level the algorithms we looked at in the first video to sort of, this kind of processing is very good for parallel processing, and it kind of, especially when you have loads of combinations, you can kind of work your way through, although it's very complicated. I don't pretend to really understand how exactly they do it. So the fact is, our brains, incredible how they are and how intelligent humans are compared to other animals. We've evolved for hundreds of millions of years, but to survive, we haven't evolved to do things like maths, computer science necessarily. We've evolved to survive effectively. So to hunt, we have very much an animal instinct, humans, which we might not like, but it's a reality. And so we don't do processing as efficiently as possible. That's why computers are much faster at doing simple processing tasks. And so if we could hypothetically replicate the human brain to make it a lot more efficient, if they were rewired, designed specifically for calculations, it would be much faster. And this is kind of what these neural networks are trying to do. So because of this kind of self-learning capacity, AI systems may be much more accurate in the way they do things. They can detect and solve problems. So I don't know if that accurate is really the right word, but in terms of solving errors themselves, in the same way that humans, when we write code, we can eventually solve errors ourselves. Whereas if a very simple computer system was doing a task and it encountered an error, it would just break, which is why we have to fix computers. Whereas AI systems can kind of fix themselves in a way, which some people might find quite scary, but in fact it might make things a lot more accurate. So there's kind of two schools of thought about artificial intelligence and autonomous machines. So probably the first AI we're going to get that's quite obvious and maybe quite scary to people is cars and lorries on the road that are autonomous. And so they can do the boring repetitive tasks that humans don't like, but it will definitely cause unemployment. The low skilled jobs, so without picking on lorry drivers, a lorry driver, apart from maybe the reversing, isn't a very probably interesting job, just driving along a motorway, whereas a robot could do this just literally all day long, 24 hours a day, so it's more efficient in that regard. So it would make our standard of living maybe slightly higher, but then in the short term at least, until these people can retrain and these industries can be removed from the economy from being very harsh, there's going to be unemployment, and so this is going to be a big ethical dilemma, I suppose, whether it's really fair to replace jobs. Even if you think in a supermarket with the automatic checkout tills, that's going to replace the cashiers, and is that fair? Well, that's something you can decide for yourself. And there's also this fear, and it's not even an irrational fear, to be quite honest. I'm going to show you two quotes in a second by two very respected people. There's a fear that AI could eventually replace humans, and very scary. Who knows how far into the future this is, or if it's even possible. Who knows if it's possible to actually replicate our intelligence. There might be something about our brains we never totally understand. I find it amazing that we even can talk about the fact that our brains aren't sufficient. If you think about it, it's pretty incredible. And there's a fear that humans could be surpassed by computers if they become super intelligent. This is the term I've seen, and this means that they exceed human capabilities and everything. So not just maths, they can do pretty much everything better than humans. If that could happen somehow, I don't know how this would ever play out, and I don't know totally whether I go along with it. I suppose it is a legitimate fear. Then if this super intelligent being could, if their goals were different to humans, if they wanted something different, in the same way that humans have made other species extinct because we're more intelligent than them, if this computer, or whatever it is, a system, became more intelligent than us, it could make the human race extinct. And so, as I say, this isn't some conspiracy theory. Stephen Hawking, very, very clever man, he it seems to be very concerned about artificial intelligence. He uses in his system some artificial intelligence, and he's talking about full artificial intelligence, so this super intelligent being. And he thinks it could spell the end for the human race. It could take on its own, redesign itself, and we would be superseded, so replaced by the computers, because we're limited by our slow biological evolution. Also know another man who's I've seen mentioned a lot in articles is Elon Musk. He owns SpaceX, which is landing rockets on ship drones and so on. He also, I think, founded PayPal, and he thinks that it's the most serious threat to the survival of the human race. So instead of climate change or anything else like that, he thinks AI is. He also thinks there should be some regulatory oversight, so there should be some international and national regulator to make sure that the ethics of artificial intelligence is kept strict. You want to make sure that it doesn't fall into the wrong hands, I suppose. And this is something you can maybe talk about if you're asked to evaluate artificial intelligence. The final and most vague emerging trend we have to look at is nanotechnology, and this is the manipulation of matter at a very small scale. And this is nano tends to be between 1 and 100 nanometers. Nanometers, these prefixes 10 to the minus 9, and most biological processes occur at this nanoscale. This is kind of the scale of atoms at the very lower end. And the quantum phenomena, the effects we were talking about earlier, start to occur at this very small scale. And so devices using nanomaterials, which are structures at this nanoscale, 1 to 100 nanometers is this nanoscale, are things like transistors. And so these can be faster, more powerful and more energy efficient by reducing them to this tiny scale. So I don't really want to talk about what a transistor is. For now, it's better to think of it as a switch, and so processors use these tiny switches. So this is a 18 nanometer wide. We have something called a drain, we have a source, and you can see made out of silicon as well. And I think I'm right in saying that the more powerful processors at the moment that are commercially available are kind of in the order of 18 nanometers, 20, 25 nanometers maybe, and we can reduce this. So IBM have actually developed, I think this is the latest I could find, this was June 2015, they've developed transistors 7 nanometers long, so instead of 18, less than half of this, something that was actually thought impossible before, because the limit, it's been found, I think Intel have said this, they found the limit of pure silicon use to be 10 nanometers. I'm not totally sure why. Everything has its limit, and so somehow IBM have managed to perhaps use an alloy to reduce this limit. So IBM say they'll be commercially ready in 2017, and they say that it will result in at least a 50% power/performance improvement for these next generation systems using a processor using these transistors. And so currently the newest Intel processors, I forget the name, they can fit 1.9 billion transistors on, which is incredible when you think about it, but actually these may be able to fit 20 billion in, which is even more incredible. And so this is going to be very powerful. Another, so different to a processor, other technology using nanotechnology is in terms of memory, and one way this is being done is using something called nanodots, which are like tiny magnets. So they act a bit like the magnetic hard disk storage we looked at, although these are much more individual units, and we have their polarity switch, so north, south, they can have that switch representing 0 and 1 to represent the binary digits. And using nanotechnology from this, reducing the size increases memory density, so you can store more data in a smaller amount of space. So those are two examples of nanotechnology being used in the computing industry. But in terms of the general fears, I suppose, one of them is that nanoparticles will be much more toxic than their sort of larger counterparts. So it could be the same material, but at this tiny scale it's much more toxic. This is because they can pass through things like membranes in our body, which we could basically gain access to our cells a lot more easily. The surface area increases, and this is why nanotechnology might be used in the drugs industry and medicine, because the surface area is made bigger because you have smaller units. Another fear is that this nanotechnology may be used to create more powerful bombs, because you're effectively shrinking everything, and so you can maximize other things. Although this is kind of a sad reality of technological progress, because if you think things like fission, I think fission came after the nuclear bomb, but research and things like radioactivity led to the nuclear bomb and so on, and it's kind of a reality. Computers came from a Second World War, they're kind of linked, unfortunately, so this is a fear you could write about. So I just thought I'd go through effectively just a summary, I suppose, talking about more about the benefits and problems. I imagine a lot of your questions will be about evaluation, so evaluate DNA computing or state the advantages and disadvantages of artificial intelligence if you get a question on it in the exam. Hopefully the notes I've made have been useful. It's not been incredibly easy, like I said at the start. I recommend you try and find out about yourself, read say 5 articles about each one if you can, and jot down some notes that if you got asked a 6-mark question, you're not sat in the exam panicking because you haven't written about it, you haven't got anything to write about. Having said that, you don't need to state, if you had a 6-mark question, it's not like you need to state 6 facts about DNA computing or nanotechnology. It's more about the holistic way you answer it. So in order you have examples and address everything asked about, so if it asks about benefits, impacts, make sure you address everything. Feel free to pause it and read what I've written here if you want to, but we've talked about it maybe long enough. Right, so for example, we'll talk about issues surrounding computing, and I just thought I would give you some prompters, maybe some ideas, just to get you on the right track, but I'm sure you're capable of thinking of your own ideas. So one ethical, perhaps, issue of computing is surrounding whether it's, so does copying equal stealing? Do you think that if you copy someone's work online, if you plagiarize, is that stealing? Is copyright claims on YouTube, is that stealing if you're using someone's music? Is it stealing when you use someone's software? Probably. These are ethical issues you might also want to talk about. Another ethical issue in, I suppose, to an extent, real life as well, not just online, is whether a victimless crime is a crime? So you could also better do this in quotes, because you could also argue there's not ever such a thing as a victimless crime. So I suppose an ethical thing that I can think of is, so I use AdBlock, and I'm sure some of you use AdBlock too. But what I do when I'm on YouTube, especially when I'm subscribed to people I like to subscribe to, people I like to watch their videos, I whitelist their YouTube channel so they can get any ad revenue that me watching the ads gives them, which isn't a lot. But I suppose, is it ethical for me to use AdBlock and stop other people making money if I'm going on their website for the first time? Maybe. Is it a victimless crime because is it going to affect them? Well, technically, yeah. So that's maybe me not being totally ethical. In terms of social issues, so unemployment is definitely an issue that affects society. So especially with not quantum, artificial intelligence, and computers are making our jobs obsolete. So that could be definitely an issue surrounding computing. Also, things like online behaviour. So you probably have had years of teachers telling you about online bullying. So let's just say online behaviour. So things like trolling. People get prison sentences for trolling people online, as it's called. Is that right? Is your online behaviour the same as it should be treated if it was in real life? Is saying something online the same as saying it in real life? That could definitely be a social issue. I suppose it also relates to freedom of speech. Should people be able to say what they want? Should they be able to say anything about politics they want? Should they be able to say something that's offensive online? Where do you draw the line? So the environmental issues should be quite clear. Maybe a less obvious one is about resource depletion. So problem is, computer systems often use tiny amounts of relatively rare resources. So copper is not used in small amounts. We use it in wires, as we've seen. But things like gold, silver are used in small amounts in things like processors. And the problem is, if you just use a small amount of gold, that's not really an issue. It's not going to reduce the gold resource. But then if you're just going to throw it out, it's going to go on landfill. Tiny bits of gold are going to waste, and eventually this is going to run out. So you might have heard about Apple making a load of money by actually extracting gold from old iPhones and other devices. So that's a really good way to do it, actually. I haven't got a problem with making money, because it means that there's not going to be a reduction in the supply of gold as much. Apart from like the emissions from using electricity, if it's generated with non-renewable resources, things like landfill, trying to recycle computers can be difficult. Parts can be toxic. And so on. So we're about to look at loads of laws, unfortunately, so we don't need to talk about this too much. I've only got blue, unfortunately I haven't got a pink. So I guess legal issues relate to things like up here. Should they be prosecuted if they behave in a certain way online? Also things about fraud. A load of fraud goes on around computers. A lot of criminal activity occurs online. And this relates, I guess, to three of these points, ethical as well. How much power should the authorities have to view online activity? Should they be able to see exactly what you're doing? That's a legal, ethical, and maybe even social issue. So the first law we can look at in the context of ownership issues, which you also need to know about. So the specification says you need to know about intellectual property, also shortened to IP. So there's two IPs in this course, and this refers to creations of the mind, like art, inventions, slogans, computer programs, to an extent. So I don't know how people defend that in court, because it's quite a loose definition, but obviously they do, I suppose, because it's protected under law through things like patents, copyright, trademarks, and usually the patents and copyright are used to protect the technology itself, whereas the trademarks is the brand name and the symbols that are used. So this is a very, very old screenshot of some Microsoft Word loading screen, just the about section, and it shows a couple of these in action. So you've got the copyright symbol that belongs to the Microsoft Corporation. Also a serial number, so same thing as a license number, and it says a license to as well. So a couple of things here we're going to have to look at. But a patent is also listed on the specification. It says that a patent gives an inventor the right to stop other people making use of their invention, and it protects how the invention works or what it does by allowing the inventor to exclude others from selling the work. That's the legal definition I've seen quite a lot while researching this stuff. And usually, especially in Europe, I've read, computer programs can't be patented. I'm not totally sure why, but apparently they can't. So you might want to bear that in mind in case you say that inadvertently in an exam question. So it doesn't actually say copyright on the thing, but the next law is the Copyright Designs and Patents Act. So I might as well say what copyright is. So this is the legal ownership applying to intellectual property, like music and films. I think you get it automatically when you for certain things like music and films, but also software can have copyright, and also anything on the internet can have copyright. So this act, shortened to CDPA, and it was an act of government in 1988, so it's been around a while now. Presumably there are provisions before as well. So this protects the intellectual property rights of individuals and organisations. That's the headline of this act. And so it makes it illegal to copy, modify or distribute software or other IP without permission. This is the one relevant to computing. It also makes it illegal to download intellectual property like music and films without permission of the copyright holder. So this is another legal issue. The fact that the internet makes music and films much more easily available. They can be illegally downloaded. It's hard to stop people downloading stuff illegally, but it is technically illegal. And we can bring in something called licensing. So most commercial software, so software that's sold for profit, comes with a license agreement specifying how the person who buys it may use a product, so how they use the software and how they can prove they're paid for it. So this kind of makes sure that you're not accused of downloading it illegally because you have this software, a license agreement which shows you've paid for it. And often a license key, so like that serial number, is often required to access the software. Bit repetitive, but just another definition of a software license. So it provides users with either paper-based or digital proof they have a right to use the software because they've bought it themselves. And you might have to enter any license keys in order to actually use the software. So generally we say software is protected by copyright unless you make it publicly available. I'm not sure how this is enforced, but it seems like you can kind of waive your rights if you make it publicly available. However, it's not just commercial software that you have to pay for. Free software also has licenses. That's maybe a bit of a misconception. So, as I say, commercial software is produced for sale, it's sold to people, and it can be either proprietary or open source. Although open source software is rarely actually sold. So let's talk about proprietary software first. So this is software that's licensed under very strict conditions, and usually it prevents you from actually modifying or distributing the software. And first of all, it prevents you from even seeing the source code. And so when you buy Microsoft Word, when you buy Windows 7, you're not expecting to see the source code because it's proprietary software. It's already been compiled to machine code, you just execute it, and you can't see the source code. So the source code is the written code on the screen that the program is written, and this isn't available. When you compile it, it gets lost. So if people could see the source code, it would be very easy for competitors or people, just anyone in general, just copy and steal the code. And so most software developers would rather not make the source code available. However, there is open source software, and this is when the source code is publicly available. And usually the license that comes with it will allow a user to study the software. Often it's used for educational purposes, also be able to modify the software and distribute it. And it makes part of the license is always to prevent other people from restricting the distribution, so it means you can't then sell this open source software. Having said that, due to this public nature, there's often little point in charging for open source software, so usually it's provided free. So it can be commercial, but it is usually free software. And the two very famous, these are both operating systems, Linux and Android, are both open source software. So the other laws we can't look at in context so much. The next one is the Computer Misuse Act, introduced in 1990, and this makes it a criminal offence to make any unauthorised access to computer material. And then the way it works, apparently, is there are kind of three conditions and they get progressively more serious. So the first one is making unauthorised access, that's the least serious. And then the second, then with increasing severity, when you have intent to commit further crimes. So if you're going into this computer without permission in order to do some other crimes, then that's a more severe offence, as you can probably imagine. But then if you also are trying to impair the operation of a computer, so a key one will be distributing viruses, that's the most serious. I don't know how many people have really been prosecuted for this. It's very difficult. Another illegal issue. How do you prosecute people, especially if they're operating in a different country, or if you don't know who they are, if it's anonymous? So this law is aimed at people commonly called hackers. The problem is, hacking was possible before or around 1990, but it wasn't as prominent as it is now, or wasn't as much of a risk. Hackers I've put in italics because hacking is got a couple of terms in computing. Cracking is a term that's sometimes used, but it sounds a bit weird to say it. And so now, because of this law, it's illegal to break into a computer system. The next law is the Health and Safety at Work Act, and that was introduced in 1974. Not a very interesting one. I had to essentially skim read the government document, which was very, very boring. So this sets out the general duties which employers have towards their employees and members of the public using their whatever they're working for, and the employees have to themselves and to each other. So really, the idea is that this act makes it a law that there needs to be this level of safety in the workplace. And so, from a computing slant, they need to ensure systems at work are safe and without risks to the user's health. So often, testing is done to ensure safety. It's not technically the law, so PAT testing is portable appliance testing, and you often see probably at your school, or if you did work experience, all the plugs have this green sticker, hopefully green. If it's red, it means it's failed. And this is, I guess, a way of protecting themselves, so people can't claim that it wasn't safe when someone has actually come in and tested it. And so people using the equipment need to have adequate information about how to use it safely and whether when it's been tested, which is why these stickers get left on. So these are a couple of points in this massive long law that are relevant to computing. So the next law is based on something we looked at in the last video, I believe, about cookies. So a web cookie is a small piece of data sent from a web server, stored in the user's web browser while the user is browsing. Just a nice recap there. So it started as a EU directive, not an act of the UK government, but it was adopted by all member states of the EU in 2011, although I feel like it sort of came into action a bit later because you started getting all these pop-ups and cookie policies start to appear. I feel like maybe a couple of years ago, so I don't know how long the delay is. So this act requires websites to get consent from users visiting the websites for them to use the cookies that store or retrieve data about them. So consent, it's not like you're saying, sometimes you'll get a pop-up saying, do you agree, yes or no? But rarely it will just be, this website uses cookies to improve your experience. And I don't know how you can turn them off. In theory, it gives people the right to refuse the use of cookies about them, but I don't know how you would still use a website without using cookies. The website would argue that you can't because cookies are used for really important features, like Amazon using the basket, probably they do that with a cookie, and so the website wouldn't work so well. So really, your right to refuse is just not to use a website. So it's a bit of a tough one, but it's the law. The next act is the Data Protection Act. This was formed in 1998. So the purpose of this is to regulate the processing of information relating to individuals, including the obtaining, holding, use or disclosure of such information. So a bit wordy, but really the idea of this is to create rights to people who have data stored about them elsewhere, so like in a company database. And so one of these rights is to be able to view the data stored about them, so you're allowed to request to see the data stored about you, also request for any incorrect data be corrected, and also requiring the data isn't going to be used for things like direct marketing. So this includes things like telesales, and also cold calls are a subset of that too. So there are 8 principles in this Data Protection Act. This is pretty much copied from Wikipedia, to be perfectly honest, although in the sort of FAQ thing at the start of the video, the example would say you don't need to know all principles of the Data Protection Act, but the bits in red and underlined sort of reinforce what we've just said, which is why I'm showing you this. So it's got to be processed fairly and lawfully, so a company can't obtain data by deception, which is probably illegal in other ways too. This one isn't really relevant, so we'll skip this. Personal data needs to be accurate and when necessary kept up to date, so this kind of refers to the fact that you should be allowed to update any data about you you don't want incorrect data being stored about you. You also have the right to access data, so you can see what they're storing about you, and as I say, check and update if it's necessary. You also need to, for people storing your data, so a company, a firm that's done some work for you, like the health service, they need to ensure that no one else can get the data without their permission, and really they shouldn't be sending it to anyone anyway. So they need security, essentially. They need things like encryption to make sure the data is only accessible to them. And the final point isn't so, well, it's about the fact that you can't transfer data to any country without adequate levels of protection to basically their own Data Protection Act. And this is outside, as they say, the European Economic Area, which is the EU, plus countries like Iceland and Norway and Liechtenstein, I think. But that's not really valid. So really, they don't want you to transfer data to countries without an adequate level of protection. So there's probably not many countries without a law like this. Maybe things like North Korea, but most developed countries would have adequate laws. So there are 3 exemptions I've seen, and that's for national security, crime and taxation, and domestic purposes. So if you have like a phone book in your household, you don't need to adhere to all of these, fortunately. But that's it for this video. Hopefully it was useful. Hopefully the videos in general were useful if you've watched all of them. I'd recommend for this topic you do your own research where possible. Make sure you have enough information for each of the points we've looked at. So the 5 laws, I think it was 5, and the 4 emerging trends. Make sure you have enough information so if you get a horrible 6 marker, you're not going to be screwed. Also, try and go into the exam with some sort of ethical, environmental, legal, social issues in your head, so you don't panic and get a mind blank in the middle of your exam, because that would be a bit of a nightmare. But anyway, I'm sure you do fine. Make sure you do all the past papers that are available, and good luck.